Ready, madam?
Yeah, sir.
Start, madam.
Okay. Hello, good afternoon, students. Welcome to the TSRJC Intermediate Chemistry classes. This is Nazia Sultana from Vikarabad. Today we will be dealing group 18th elements. Okay, you already know that group 18th element, it consists about the noble gases. What are the noble gases? The noble gases are helium, neon, argon, krypton, xenon, and radon. Okay, radon is a radioactive element. That means its half-life is very less. For that reason, it is not mentioned over here. Yeah, what are those? Let us see here. Okay, group 18 elements, it consists of about 6 elements. Okay, already just now I have said helium, neon, argon, krypton, xenon, and radon. And why are we calling them as noble? Because they do not react. Okay, what is the reason why they are not able to react is they are having fulfilled configuration in their outermost shell. Okay, they have 8 electrons except helium. Helium has 2 electrons in its outermost configuration. Okay, in its outermost shell. So we say that helium has duplet configuration, whereas for the remaining noble gases, okay, what are the remaining noble gases? Neon, argon, krypton, xenon, and radon. They have 8 electrons in their outermost shell, also called as valence shell. Okay, because they are having the octet configuration, they do not tend to react. They do not react. And for that reason, we call them as noble gases. Okay, and noble gases are also called as zero group elements. Okay, why are we calling them as zero? Because their valency is 0. So what is valency? Valency is the combining capacity. Okay, so because of the duplet configuration and the octet configuration, okay, they do not react. That means that combining capacity is 0. But later on this was disproved because we are able to make xenon to form the compounds. That is another theory. Okay, and these are chemically unreactive. These gases are chemically unreactive. Okay, they form very few compounds. Because of this, they are termed as noble gases. And what is the source to obtain these noble gases? These noble gases are generally extracted from the air only. Okay, by the fractional distillation of liquefied air. We can obtain these noble gases. Their atmospheric abundance in dry air is about 1%, less than 1% by volume, of which argon is the major constituent. So this is important. So among the noble gases, argon is the major constituent of the air. Okay. And just now I said about radon. Radon is a radioactive element. Okay, radon is obtained as a decay product of radium. Okay, we know that radium is a radioactive nuclide. That means what? It, because of the heavy nucleus, it splits into 2 or more different elements. That is what is called as radioactive disintegration. So why does this happen? To obtain the stability. Okay, radium is unstable. So what happens is it is splitting into radon and helium. This is an important bit once asked in your competitive exams. So you need to learn this. Okay, radium upon radioactive decay, it gives radon whose atomic number is 86 and mass number is 222. And gives helium also. Okay. Yeah. So now let us see the atomic and physical properties of the group 18 elements. The general electronic configuration is ns2 np6 except helium. Just now we said now helium has duplet, whereas the remaining noble gases have octet. 2 plus 6, 8. 8 electrons in the valence shell is called as octet configuration. Okay. Next, ionization enthalpy. Okay, So what we need to know is that these elements, they are having octet configuration. That means it is a very stable configuration. So the atom doesn't tend to either lose the electron or gain the electron. So if you want to remove the electron, that is what is ionizing. If you want to ionize it, you have to provide very large amount of energy to remove the electron. Okay, or else the atoms will be gaining the electron. That is okay, whenever we are adding an electron to an atom, what happens? Energy is released. That energy is called as electron gain enthalpy. Okay, so noble gases, they neither lose the electron, they neither gain the electron. If you want to carry out either the ionization or add the electron to it, we have to provide large amounts of energy. Okay, so these noble gases, they are having high ionization energy, and ionization energy decreases down the group as usual. This is a usual property. Yeah, next coming to the other property, that is atomic radius. Okay, the atomic radii increase down the group. So as we move down the group from helium to radon, what happens? Due to the addition of an extra shell, the atomic size increases. Okay, that is normal thing. Next, coming to the electron gain enthalpy. Yeah, just now I said now, whenever we are adding an electron to the atom, energy will release. So in the case of the noble gases, if you try to add an electron, what happens is, instead of the energy being released, we have to provide excess of energy. So here, due to stable electronic configurations, they have no tendency to accept the electron, and therefore have large positive values of electron gain enthalpy. That we need to know. Hope you have understood this. Okay, generally electron enthalpy is negative. That means heat is released. But for the noble gases, if we add an electron, we have to provide the energy so that the atom accepts that electron. Yeah. Next, let us see the other physical properties. So all the noble gases are monoatomic. That means what? The single atom itself is stable over here. Okay? Because their valency is 0, they do not combine to form the molecule. So hence, the atom itself is stable. So we have to call it as monoatomic molecules. So these are the only elements where we see monoatomic molecules. Okay? And these noble gases are colorless, odorless. Odorless in the sense they do not have any smell, and they are tasteless. Okay? They are sparingly soluble in water. That means very little soluble in water. They are insoluble, generally insoluble, or we can say it as sparingly soluble, soluble to a little extent. They have very low melting points and boiling points, because the only type of interatomic attraction in these elements is weak dispersion forces. That means what? Between these, actually in between the molecules, we see the attractive forces. Okay, you have already learned different types of attractions between the molecules in the first year. London dispersion forces, dipole-induced dipole interaction. There are so many interactions, but in this case, only weak dispersion forces are there. And because the dispersion forces, only one type of dispersion forces are there, and that too they are weak, they are having very low melting and boiling points. Okay, and helium has the lowest boiling point of any known substance. So this is an important bit over here. Helium has the lowest boiling point, and its boiling point is about 4.2 Kelvin. Yeah. So this is the graph of the noble gases showing their melting and boiling points. Yeah. Next, coming to the chemical properties. In general, noble gases are least reactive. We said, na, because of the stable configuration in the outermost shell. So except helium, all the Other gases, that is neon to radon, they are having 8 electrons. They have octet, whereas helium has duplet. Okay, and they have high ionization energy and more positive electron gain enthalpy. Okay, so actually what is reactivity? Gaining the electrons or losing the electrons, that is what is reactivity. So whenever an element is gaining the electron, the other element accepts it. So in doing so, they form the compounds. Okay, here these noble gases, they are neither losing the electron nor gaining. So that is the reason why they are unable to form the molecules or the other compounds. Yeah. But in 1962, okay, a scientist called as Neil Bartlett, then at the University of British Columbia, prepared a red compound formulated as O2PTF6. This is dioxygen platinum hexafluoride. Okay, he has prepared this compound. Okay, while preparing this compound, what we have to notice over here is oxygen is getting the positive charge. That means what? We are removing the electron from the oxygen. So what he has noticed is, if the same amount of energy is given to remove the electron from xenon, xenon can form an ion. He has noticed that. So he realized that the first IE, ionization energy of oxygen, is 1175 kilojoule per mole. And this is almost identical with that of xenon. Okay, what is the ionization energy of xenon? 1170 kilojoule per mole. That means these two values are somewhat closer. So if this much amount of energy is given, that means the electron of xenon can be removed. That he has noticed. And after noticing that, what he has done is he made same type of another red color compound, that is xenon platinum hexafluoride. Okay, he prepared this by mixing platinum hexafluoride, PTF6 and xenon. So see here, xenon is reacting with the platinum hexafluoride at room temperature and forming xenon platinum hexafluoride and xenon diplatinum hexafluoride. These two are being formed. Okay, after this discovery, a number of xenon compounds, mainly with most electronegative elements like fluorine and oxygen. Yeah, we know that the most two electronegative elements are fluorine and oxygen. First is fluorine, then comes oxygen. So only these two elements are able to react with the noble gases, and that too which one? Xenon. So xenon is able to form the compounds with the most electronegative elements, that is fluorine and oxygen. So let us see the xenon fluoride compounds. Okay, xenon is able to form 3 types of fluorides. Okay, what are those? XCF2, xenon difluoride, XCF4, xenon tetrafluoride, and XCF6, xenon hexafluoride. Okay, so these are the 3 important xenon fluorine compounds. These compounds are very, very important. You have to learn their structure, the hybridization of the central atom, okay, the number of lone pairs and bond pairs present, because these are the important bits asked from this chapter in your competitive exams. As well as for 4 marks also, these can be asked. How do we prepare the xenon fluorides? So let us see here. Preparation. Okay, by direct reaction of the elements. That means what we have to do, we have to take xenon and fluorine and make them react under appropriate experimental conditions. So let us see here. Xenon and fluorine, when they are reacting in 2:1 mixture, when they are reacting in the ratio of 2:1, we would be getting xenon difluoride. Okay, here what we have to see, we have to maintain the temperature of about 673 Kelvin and 1 bar atmospheric pressure. Okay, So we will be getting xenon difluoride. Next is xenon tetrafluoride. So when do we get this? When we are taking the mixture of about 1:5 ratio, 1 part of xenon and 5 parts of fluorine, and the temperature has to be slightly increased over here. Okay, 873 Kelvin and 7 bar. So we will be getting xenon tetrafluoride. Okay, and same mixture, but here the ratio is changing. 1:20 parts. 1 part of xenon and 20 parts of fluorine when we are taking. Okay, and the temperature about 573 Kelvin and 60 to 70 bars. Here the pressure is much more. Okay, at this pressure we are getting xenon hexafluoride. Okay, next let us see the properties. Hydrolysis. Hydrolysis means what? Reaction with water. Okay, they're readily hydrolyzed even by the traces of water. That means even when small amount of water is present, xenon fluorides, they react with the water and liberate HF and oxygen, and they also give xenon. This is very, very important. Xc, HF and O2 are the common products. Okay, so whenever xenon fluoride is reacting with the water, we get xenon, hydrofluoric acid, HF and oxygen. Yes. Next, see the another reaction, xenon tetrafluoride. So when xenon tetrafluoride is reacting with the water, okay, it forms xenon. Same, the two products are same here. You see, xenon here also xenon, HF, HF, oxygen, oxygen. Here one extra product. What is that extra product? XCO3, xenon trioxide. Okay, this is important over here. So whenever xenon tetrafluoride and hexafluoride, they are reacting with the water, we are getting XCO3, that is xenon trioxide. Okay, this is an explosive solid. That means what? It will be exploding like a bomb. This is an explosive solid. These two things you have to remember. So whenever xenon tetrafluoride and xenon hexafluoride are reacting with the water, we get xenon trioxide. This is an explosive solid that you have to remember. Practice these equations. Yeah, next thing. Xenon fluorides react with fluoride ion acceptors. That means the substances whichever accept the fluorine ion, they are called as fluoride ion acceptors, to form cationic species and fluoride ion donors to form fluoroanions. So let us see what it means. You see, xenon difluoride, XCF2, it is reacting with PFI, phosphorus pentafluoride. That means this phosphorus pentafluoride, it can accept one more fluorine from XCF2. So what is happening? XCF plus, it is forming a cation, and PF6 minus. Okay, so PFI is fluoride ion acceptor. Okay, and they are forming the ionic species. The same thing here. XCF4, when it is reacting with stilbium pentafluoride. Okay, so what is happening? What is the change you are noticing? See here, one F from XCF4 is added to SBF5. So what happens? It becomes SBF6 minus, and this becomes XCF3 plus. That you have to understand. Similarly, instead of any particular element, we are taking as general element, MF. Okay, XCF6, it is reacting with a metal fluoride. M can be any metal. Okay, what happens is it becomes M plus XCF7. So this fluorine from the metal is taken up by this XCF6. So it becomes XCF7. Okay, and we know that metals will be losing the electron. That electron is taken up by this species. So it forms M plus XC7 minus ion. Yeah. Now let us see the structures of xenon fluorides. So this is very, very important, ma. Please make a note down of it and as well as practice these diagrams. Okay. So you know that xenon has 8 electrons in the valence shell. So in the formation of XeF2, that means what? 2 bonds have been formed by xenon. That means first xenon F difluoride is formed when xenon undergoes first excited state. That means after first excitation, there will be 2 unpaired electrons and remaining 6 electrons would be the lone pairs. Okay, see these 3 pairs. These 3 pairs are the lone pairs and these 2 purple colors are the bond pairs. Okay. So what is the hybridization over here? sp3d. And the structure is linear. The molecule is linear. Okay. Next, coming to the xenon tetrafluoride. 4 fluorines are there. Okay. Upon first excitation, there would be 2 unpaired electrons. Upon second excitation, there would be 4 unpaired electrons. So XeF4 is formed when xenon undergoes second excited state. Okay. So there would be, upon second excitation, there would be 4 unpaired electrons. So they will be pairing up with 4 fluorine atoms and forming 4 bonds. And remaining 4 electrons would be present as lone pairs, 2 lone pairs. Okay. And actually, because whenever sp3d2 hybridization is there, what should be the geometry? The geometry should be octahedral. This you have learned in first year itself. Okay, whenever sp3 hybrid, Vesper 3 valence shell electron pair repulsion theory, you have learned it. Okay, so whenever the sp3d2 hybridization is there, the geometry should be octahedral. But in this case, because of the presence of 2 lone pairs, the shape is changing from octahedral to square planar. So what is the shape of XeF4? Square planar. This you have to keep it in your mind. Yeah, next coming to XeF6. F6 means what? Xenon should form 6 bonds with 6 fluorine atoms. Okay, that means it should have 6 unpaired electrons. So number of excited states required is 3. So whenever xenon undergoes 3 excitations, okay, it will be having 6 unpaired electrons and 2 electrons would be present as the lone pair. Okay, so XeF6 has 6 bond pairs and 1 lone pair. Okay, and what is the hybridization? Hybridization is sp3d3 and the geometry is distorted octahedral. Okay, this is very, very important. So the structures, the hybridizations, the number of lone pairs and bond pairs are very important from the compounds of xenon. Yeah. Now let us see xenon oxygen compounds. Just now we have seen XeO3. This is formed when XeF4 and XeF6 are reacting with water. Okay. So total of 3 compounds. What are those? Let us see. XeO3, XeOF4. XeOF4 means xenon oxide tetrafluoride. Okay. Xenon dioxide difluoride. That is XeO2F2. So these 3 xenon oxygen compounds are formed. So let us see XeO3. XeO3 is nothing but xenon trioxide. So this is formed when xenon tetrafluoride or xenon hexafluoride, they react with the water. So let us see here. XeF4 is reacting with the water and forming xenon trioxide, HF and O2. If you practice this equation as the chemical properties of XeF4 and XeF6, you will get this. Okay. And similarly, xenon hexafluoride is reacting with the water and forming XeO3 and HF. XeO3 is the explosive solid. This you have to remember. See here, XCO3 is a colorless explosive solid and has a pyramidal molecular structure. So actually, what is the hybridization? We have to see this. No, whenever double bond is there, only one we have to consider, because hybrid orbitals do not form the pi bond. So 1, 2, 3 plus 1, 4. So 4 hybrid orbitals are present. So if 4 hybrid orbitals are present, what would be the hybridization? sp3. If sp3 hybridization is there, what should be the geometry? Geometry should be tetrahedral, but here it is pyramidal because of the presence of lone pair. Okay, this you have to remember. Yeah, let us see the other oxides. Xenon oxy tetrafluoride and xenon dioxy difluoride. Yeah, see here. Partial hydrolysis of xenon hexafluoride gives oxyfluorides. Xenon oxy tetrafluoride and xenon dioxy difluoride. So see, xenon hexafluoride upon reaction with water, what does it give? Xenon oxy tetrafluoride, XeOF4 and 2HF. These reactions you have to learn as it is, man. And XeF6, it reacts with water. One more here, when we are comparing these two, here the number of water molecules are more. So when it is reacting with a bit more amount of water, it is forming xenon dioxide difluoride, XeO2F2. Okay, here these products are same. HF is common in both of these. Yeah, see here. Xenon oxy tetrafluoride, XeOF4, is a colorless volatile liquid and has a square pyramidal molecular structure. So here the structure is important. It has square pyramidal molecular structure. So that is about xenon oxy tetrafluoride. So let us see the shapes over here. Yeah. Xenon, 4 fluorines, 1 oxygen. So XeOF4. Okay. So how many excitations are required? 3 excitations. Upon 3 excitations, there would be 6 unpaired electrons. So single bonds with fluorine and oxygen forms a double bond. Okay. So what is the hybridization over here? So whenever a double bond is there, we have to consider only one, that is a sigma bond. That sigma bond is formed by the hybrid orbitals, right? So 1, 2, 3, 4, 5, 6. So 6 means sp3d2. Even the lone pair orbital we need to count. Okay, sp3d2 hybridization. Okay, whenever sp3d2 hybridization is there, it should be octahedral geometry, but it is square pyramidal because of the presence of lone pair. Repulsions would be there between the lone pairs and bond pairs. Because of that, the geometry, instead of being octahedral, it is square pyramidal. That you need to know. Okay, next, XeO2F2. Okay, even this needs 6 unpaired electrons because 2 bonds with 1 oxygen, another 2 bonds, total 4, again 2 fluorines, so total 6 electrons, 6 unpaired electrons. In order to get 6 unpaired electrons, xenon has to undergo 3 excited states and 1 lone pair. So here, what is the hybridization? You see, we have to count this one: 1, 2, 3, 4, 5. So whenever 5 hybrid orbitals are there, means we should write the hybridization as sp3d. Okay. And what is the shape here? It is appearing like the seesaw. So the shape over here is seesaw shape. Okay. So this is very, very important. So the structures, geometries of the compounds of xenons are very, very important. Yeah. Next, let us see the uses of the noble gases. Already you have learned in the chapter solutions, okay, about the applications of Henry's law. What are the applications of Henry's law for packing the soda water, that is carbonated drinks? Again, as well as helium is used as a diluent for diving apparatus, okay, because helium is less soluble in the water. It has very low solubility. It doesn't dissolve in the blood. For that reason, we are using helium as the diluent in the respiratory apparatus used by the scuba divers. Okay, let us see what are the uses of helium. Helium is non-inflammable. That means it does not catch fire. Okay, and light gas. And because of this reason, non-inflammability and being light in weight, helium is used for filling the balloons for meteorological observations. So what are meteorological observations? Okay, for studying the weather forecasts, right? So they'll be using the balloons which are using helium gas. Okay, next, helium is used in gas-cooled nuclear reactors. Okay, liquid helium finds use as a cryogenic agent. So what is cryogenic? Cryogenic means cryogeny is related to the lower temperatures. Cryoscopic constant, ebuloscopic constant, these you have learned in solutions again. Okay, so cryoscopy is related to the lower temperatures. So because helium is having very less boiling point, it is used as a cryogenic agent. Okay, so it is used for carrying out the experiments at low temperature. It is used to produce and sustain powerful superconducting magnets, which form an essential part of modern NMR spectrometers and magnetic resonance imaging, MRI. Okay, NMR means nuclear magnetic resonance. Okay, so we'll be taking MRI scan, CT scan, all this, right? So for taking such scannings, we need superconducting magnets. So how is it produced? By using the helium. Okay, and another thing, it is used as a diluent for oxygen in modern diving apparatus because of its very low solubility in blood. Yeah, we have learned, no? So helium, it has very low solubility. What happens if we do not use helium? Nitrogen would dissolve in the blood. Okay, and it will lead to bends. Bends, it may cause death, right? So to prevent that, we will be using helium as a diluent for oxygen in modern diving apparatus. Yeah. Next is neon. Neon is used in discharge tubes and fluorescent bulbs. Okay. So what are fluorescent bulbs? We are using CFL, compact fluorescent bulbs, right? So for advertisement purpose, for getting the bright colors, we would be using neon. And neon bulbs are used in botanical gardens and in greenhouses. So this is important bit. It is used in botanical gardens and greenhouses. Okay. So greenhouses are used to grow the plants, right? So there we will be using the bulbs, neon bulbs. Next, coming to the other gas, that is argon. It is mainly used to provide an inert atmosphere, okay, in high temperature metallurgical processes. So what are metallurgical processes? These are related to the extraction of the metal. So whenever we are extracting the metal, we will be having very high temperatures, right? So whenever the temperatures are more, there is a chance that other elements will react, right? So the atmospheric gases may react. So in order to prevent that reaction, we will be using argon to give the inert atmosphere. Okay, it is used to provide an inert atmosphere in high temperature metallurgical processes. And for filling electric bulbs. Okay. So this is a very important bit. Actually, the electric bulbs, they used to be spoiled. Who invented the electric bulb? Thomas Alva Edison, right? So oxygen would be reacting. If we are generally filling the electric bulbs with the air, oxygen might oxidize the filament. So instead of filling the bulb with the air, we have to fill it with argon because it will be giving the inert atmosphere. It doesn't react with the filament of the electric bulb. Okay. Let us see the another use. It is also used in the lab for handling substances that are air sensitive. Okay. So because of the whichever are air sensitive, right, they might react with the air. So for getting the inert atmosphere, we will be using argon. Next is xenon and krypton. There are no significant uses of xenon and krypton. Okay, they are used in light bulbs designed for special purposes. That means they are used in the lights only. Yeah. So let us see some of the important questions related to this topic. Okay, why are noble gases inert? Okay, we already know that they are having octet configuration. Because of the octet configuration, they are inert. Okay, name the noble gas which has only duplet configuration, that is helium. That also you need to keep in your mind. Okay, next to see the important structure. These are the questions which are important for your IPE as well as for your competitive exams. In that sense, I have given. Okay, name the structures of the following compounds, draw their structures as well as mention the number of lone pairs and bond pairs. Yeah, generally in the competitive exams, they will ask you about the number of lone pairs as well as bond pairs. That also you have to find out. So practice the structures. Okay. We have discussed this one. Next question you see. Why is helium used in diving apparatus? Yeah, because of its low solubility in the blood, helium is used as the diluent. Next question, write the radioactive decay of radium. Okay, we know that radium, it would be disintegrating or it will be giving radon, whose atomic number is 86 and mass number is 222, and helium. Okay, that is the reaction. Next, why is the electron gain enthalpy of noble gases positive? Generally, electron gain enthalpy is negative, right? Because of the stable octet configuration, they do not accept the electron. Hence, they do not have the, actually we do not discuss the electron enthalpy. But even if we are forcibly trying to accommodate an electron, we have to provide extra energy. Okay. So for that reason, they have very high positive enthalpies. Next, how are XCO3 and XCO4 prepared? Yeah, we know that XCF4 and XCF6, xenon tetrafluoride and xenon hexafluoride, they react with the water and form XCO3. That you have to practice. Okay, and XCF4 is also prepared in the same way when the amount of water is changing. Hope you have understood. Please go through the textbook and practice the structures, draw it, what is the configuration, what are the, how many excited states are required, that you have to practice for your IPE. You can go through this. Please practice these structures. Note it down. These are the uses of noble gases. With this, the chapter is done. So let us have a quick review. Yeah, these are the gases. This is very, very important. Radium. Radioactive disintegration of radium gives radon. This is important. Their ionization energies. Why their electron enthalpy is large? Because of stable octet. Their physical properties. Here they can ask you, why are the boiling melting points and boiling points very low? Because of weak dispersion forces. Okay, their chemical properties. Helium has duplet configuration. Actually, helium is totally inert. That means it doesn't at all react. Okay. And what made Neil Bartlett to prepare xenon compounds? Actually, the formation of this compound, dioxygen platinum hexafluoride. Upon synthesizing this, he came to know that the IE value, ionization energy of xenon is similar to that of the oxygen. Based on that, he has synthesized. These are the xenon fluorides. Xenon difluoride, xenon tetrafluoride, xenon hexafluoride. Okay. And properties of xenon fluorides. They are powerful fluorinating agents. That means they will be adding fluorine to a compound. Okay, they will be releasing fluorine, and that fluorine will be reacting with the another compound. So they are powerful fluorinating agents. And see this chemical properties: xenon difluoride, tetrafluoride, and hexafluoride. They will be reacting with the small traces of water and forming xenon hydrogen fluoride, or hydrofluoric acid also you can say, hydrogen fluoride, oxygen. And here this is important, XCO3 is formed when XCF4 as well as XCF6 they react with the water. So we will be getting XCO3. This is an explosive solid. Yeah, xenon fluorides, they also react with the fluoride ion acceptors. Yeah, this one you see. This PFI can accept one more fluorine from XCF2. SBFI can accept one more fluorine from XCF4. So these are the fluoride ion acceptors. So structures of xenon fluorides. XCF2 is linear, XCF4 is square planar. Okay. And XCF6 is distorted octahedral. So number of lone pairs, bond pairs are very, very important along with the structures. Here we are having 3 lone pairs, 2 bond pairs. Here 4 bond pairs, 2 lone pairs. Here 6 bond pairs and 1 lone pair. Coming to XCO3. It is formed when XCF4 and XCF6 they react with the water. Okay, XCO3 is formed. What is the unique nature of XCO3? It is a colorless explosive solid and it has pyramidal molecular structure. Okay. And see XCOF4 and XCO2F2. So here one thing what I would like to say is, generally oxygen will be having negative oxidation state, but only when it combines with fluorine it will be having the positive oxidation state. That you need to know. So xenon hexafluoride, when reacts with little amount of water, it forms xenon oxy tetrafluoride. Okay, when it reacts somewhat more amount of water, it forms xenon dioxy difluoride. This is the difference you need to know. Here one water molecule, here 2 water molecules. Okay, XCOF4 is colorless volatile liquid. and it has square planar molecular structure that you need to know. Yeah, these are the shapes, or we can say the geometries and hybridization of XeO-F4 and XeO2F2. This shape is very, very important. XeO2F2, it has seesaw shape. Yeah, we have also seen the uses of the noble gases. So please go through the textbook and learn. Sir, shall I wind up?
Yes, madam.
Okay, sir. Right. So please go through the textbook, students. This is also very, very important. 4-mark question can be asked from this. Okay. And competitive bits based on the molecular structures, lone pairs, bond pairs of the compounds of xenon and oxygen and fluorine. These are asked. Compounds of xenon fluorides, xenon oxygen fluorides. These are asked. Okay, sir, done.